All right, so I am just going to run through real quick and talk with you a little bit about what we got going on in 5.02, understanding and approximating irrational numbers. So we're just going to jump right on in to our, oh man, hold on. Hold on. We're just going to jump through. We're not going to do all of these just yet. All right. So we're going to go ahead and jump right into our key concept. So one of our key concepts today is that we've got some square roots going on. Hopefully you've heard of square roots before, maybe even if you just, oh, I think I know what that is. So this is something that should be sort of familiar to you. So you want to remember that the square root of a perfect square is the factor that multiplies itself to equal the perfect square. And all that means is that a square root is a whole number, and when we multiply a whole number by another whole number, we should get a perfect square. All right. Oh, goodness gracious. All right. One example of a square root is the square root of 36. So we're thinking to ourselves, is there a number that when multiplied to itself would equal 36? Well, yeah, 6. I can multiply 6 by 6 to get 36. So the square root of 36, we write it as square root of 36 is 6. All right, pretty simple there. All right. So when we think about our perfect squares and square roots, we've got our inverse operations here. So in expanded form, we've got 1 times 1 equals 1, 2 times 2 equals 4, 3 times 3 equals, oh goodness, 9, and so on and so forth. So you can look through this table and try to work through it together, work through it independently, and see if you can figure out, okay, what's going on here, and how can I figure out and make sure I know what the expanded form of a number squared looks like and what my answer is. And then you can also work backwards. So the square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, and so on and so forth. And see what you get going on over here and see if you can find a relationship between these two. All right. So what if we get a square root like the square root of 23? Well, we can scan back through a list of what we know. Think back on what we know. We know that the square root of 23 is going to be some number times itself. So we can call that x times x. All right, so let's start at 4 times 4. Well, 4 times 4 is 16, and that's less than 23. What about 5 times 5? Well, 5 times 5 is 25, and so that's higher than 23. So since there's not a whole number that can be multiplied to itself to get 23, then the square root of 23 must be a number somewhere between 4 and 5. All right, so let's now type it in our calculator. What is the square root of 23? Pulling out my handy dandy calculator. Square root of 23 in our calculator. Well, I don't know about you, but I get 4.79583153. All right. So, and then I'm out of space on my calculator. So then it says, does that number appear to have a terminating decimal? Does the decimal have any repeating patterns? It really doesn't look like this number ends, honestly. It looks like it would just keep going on if my calculator had room. And the decimal doesn't have any patterns that I notice yet. So what does that mean? We've talked about a terminating decimal, a decimal that ends, that has a finite number of non-zero digits to the right of the 0. And we've talked about repeating decimals like 0.33333, so on and so forth, forever and ever. But we've not talked about one that doesn't terminate and doesn't repeat. So we're actually going to be talking about something new today. Today we're going to be talking about irrational numbers. So we've talked about rational numbers. Those are numbers that can be expressed as a fraction, and they include terminating decimals and repeating decimals. So decimals that have a finite number of non-zero digits to the right of the to the right of the decimal, and repeating decimals. So we've got some examples of those down here. So if you need to take a couple minutes and look over this vocabulary, go ahead and take some time to do that. I'm going to keep moving forward in 3, 2, 1. All right, so the main things we want to pull from here is that a rational number is a number that can be expressed as a ratio or a fraction, right? So a ratio can be expressed in fraction form, a over b, where a and b are integers, and b cannot equal 0. That's supposed to have a not sign in there. Or it can be written in decimal form. A non-repeating decimal continues forever with no pattern of repeating digits. These are classified as irrational numbers. So a non-repeating, non-terminating decimal is called an irrational number. An irrational number is a number that cannot be written as a fraction. You guys should love that since you hate fractions. So ta-da! Irrational numbers are numbers that cannot be written as a fraction. So in the past, I'm sure that you have gone through and thought about the organization of numbers. So we can start with natural numbers, and those are numbers that you can count on your fingers and toes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth. All right. Then we move out just a little bit, one level, and we get to whole numbers. Whole numbers are all natural numbers plus 0. All right. Next, we move on to our integers. Integers are all whole numbers, so 0 and then all positive numbers, and the negative numbers, the negative opposites of our natural numbers. So -4, -362, all that. Rational numbers, that's where we find our fractions and our decimals and our non-terminating decimals are decimals that are repeating. And so that's where we're going to find our rational numbers. Integers, whole numbers, and natural numbers all fall under the category of rational numbers. All right. So they also, all of those definitions we just talked about fall under the category of real numbers. All right, so a separate category that we have under real numbers, so all of this is under the umbrella of real numbers, is our irrational numbers. Irrational numbers, once again, are numbers that cannot be written as a fraction. When you take the square root of a number, if it's not a perfect square, you can consider that an irrational number. Okay, if it is not a whole number, when you find the perfect square, when you find the square root, so if it's not a perfect square number, then that is an irrational number. All right, the number pi or the value pi is an irrational number because it goes on forever and ever beyond the 0 and never ends. All right, okay, so feeling okay about this? I'm going to go ahead and if you need to pause, you can pause right here. I'm going to go on in 3, 2, 1. One thing that you need to note is if the square root of a number is given and the number is not a perfect square, then the square root of that number is always irrational. Once again, if the square root of a number is given, so for example, square root of 51, and the number is not a perfect square, then the square root of that number is always irrational. Okay. So let's do a quick check here. If the square root of a whole number is not a whole number, the square root is irrational. Remember that. So right now I want you to pause the recording and I want you to classify these numbers as rational or irrational. All right. I should have gone through and highlighted these earlier, and I'm so sorry that I did not, but I'm just going to point and show you which numbers are rational and which ones are irrational. Pi, as we've already discussed, is an irrational number. This 8.245, so on, is irrational. 6.2 repeating is rational. 4/5 is rational. -28 is rational. Square root of 64 is rational because that's 8 times 8. This number is rational because it's repeating, and square root of 99 is irrational. I'm going to go ahead and stop this recording now and pick up with our next concept in a moment.